Hello and welcome to our video presentation for this week. Hope you enjoy. So it is all about simple call returns, recursive procedures, and coroutines. First, let's talk about simple call returns. Simple call returns is the simplest type of procedure. This because it is straightforward, very simple, and it plays the fundamental characteristics of every other type of procedure. This procedure utilizes a call, which is what we talked from the past lectures, a call which is the one that passes the control to a certain subroutine or function. So it calls a callee, and a return which lets the control return to the calling program. To execute a simple call return, there are two types of methods to use. First is the copy rule method, and second is the memory allocation. These two methods will be discussed in the later slides. Let's first talk about copy rule method. In this method, a copy of the procedure is created to replace the procedure, ensuring that all substitutions are suitable in terms of parameters and identifiers. This method is used by earlier languages like Fortran and COBOL. Before we tackle an example, let's talk about the issues behind copy rule method. These issues are mostly because of the type simplicity. So first is it cannot be recursive. If it happens to be recursive, there will be an unending copying of the procedure, which we like to avoid. Second, it requires explicit call statements. All call statements are needed to be clearly stated for the copy rule method to work. Third, procedure is executed completely. Before calling another procedure, the existing procedure must be executed completely. Number 4, immediate transfer of control at every call. Other types of procedures promote delayed control transfer, which is not the case here in this procedure. And lastly, single execution sequence promotes the third issue, which is that the procedure is executed completely. So it is straightforward and single-threaded. So we could see here there is an example of a copy rule method that we took from the PPT given, the pre-made PPT given in the VLE. So we could see here there is a call, this call, and there is a return, this one. So it traverses here first, and whenever it sees a call instance, it will proceed to call the procedure specified, which is here, and it will execute the procedure. So every part of it. So here you could see it is traversing through the procedure, and every statement, every part of the procedure is done. This one is executed, and then it traverses to the next one. It traverses this one, and after all the statements are executed of the procedure, it will go into a return. This return will give the control back to the call, wherein it knows that the call is done. Then it will go and traverse once again to find another call instance until its last. Let's move on to memory allocation. In this method, it shows how the machine deals with the procedure execution while utilizing its memory. It uses a procedure activation, which we will talk later on, and the procedure definition is translated into a template for easier access for activation. A procedure activation uses a code segment, which is the executable code, and an activation record, which is used to manage the information, which includes the local variables needed by a single execution in the procedure. This procedure is managed by using a runtime stack. I hope you could recall this from the earlier lectures we've had. As you could recall from the earlier lectures, the execution is managed by the use of system-defined pointers. So first, current instruction pointer points the address of the next statement. And second is the current environment pointer, which points to the activation record. So let's talk about how memory allocation works. So first, let's talk about the activation record. Here. So the activation record is created when the call is made. So you can see here the parameters used for execution and the return address. The activation record will then be pushed to the stack. As we could see here, you see here the main activation record and a sample activation record. Okay, so let's dig deeper and use an example. As you can see here, a blank stack, a sample stack, and here is an example of the program. See here, main calls call A, main calls call B, and call B calls call A. Okay, so let's start with main. So main will be pushed to the stack. Let's put here. Okay, main, it's readable. Okay, then while the machine reads through main, it sees the instance of call A. So we make an activation record for call A and push it to the stack. Let's make call A. The control goes to call A. After reading call A and executing it, then call A will then be popped out of the stack. Then the control goes back to main. As the machine continues to read main, it sees another instance of a call. So it's call B. So an activation record will be created and call B. Let's add here. Okay. Call B will be created. This one. Okay. Then while reading call B, it sees a instance of a call A. So we see, so we make another activation record for call A. So while reading call A and executing it, so call A will be popped off right after. Then the control goes back to call B. So while reading call B again, it will be popped after execution, and the control goes back to main. After the machine sees nothing anymore, any calls, there are no calls anymore, the main will also be popped off and the program is finished. So we could see here its potential to other types of procedures like recursion. So let's move on to recursive procedures. So recursion is a very powerful technique for algorithm design simplification. A procedure that creates another activation of the procedure while actively executing the first one, or on the first activation's runtime. It has two paths, a path for recursion and a path for termination. Consider that the path of termination is very important because it ends the recursion. Without it, it will go into an infinite loop. So there are two types of recursive procedures. First is the direct or the conventional one. The call directly calls within the same original call. In this, the similar second call is within the execution of the original call. Second is the indirect or the unconventional one. In this one, there is an intervention of another procedure to call the original call. So a call calls another procedure that calls the original call. So it creates a cycle. Even though recursion simplifies the algorithm, it does not mean it is recommended every time. There are issues involving recursive procedures. First, it takes up too much space. It takes too much space whenever more instances of procedure are used. The more recursion made, the more memory is used every time. Second, the problem of clarity. It is harder to keep track on the execution compared to simple procedure flows. So we could see here an example of a code segment for recursive procedure. So you could see here the main and the call A, and you can see here that main calls call A, then it will go to the call A to execute it. Then we can see that call A calls itself, which will then call itself. There we could see a recursion happening. This is straightforward direct recursion. So if we want an indirect recursion, let's add another call. So here, let's make an example. Let's draw another example. So let's call it B, and it calls A. Pretty hard. Let's call A, and this one will call B. So you can see here that when call A is called, it will go to B, while B will call A. So it go to A. As you can see here, there is a cycle happening. This one, there's a cycle happening, which means an indirect recursion has been made.
Now let us proceed to coroutines. It is a procedure that may transfer control to another procedure even though the whole procedure is not completely executed yet. The next time control is returned back to the procedure, the execution continues from the first unexecuted instruction. Now to further explain coroutines, as you can see, the word coroutine is made up of two words. The first word is co and the second word is routines. Co can be expanded into cooperatives and routines can be expanded into functions which we use in our day-to-day programming. So you must be wondering what is meant by cooperative functions and how functions cooperate with each other. To properly understand what function cooperative is, we first need to look how functions work without cooperations. For example, let us consider that we have a function called a function, and which is calling b function which does 1, 2, 3, 4 things. When a function calls b function, the b function will do all the 1, 2, 3, 4 job before the control returns a function. There is no passing of control in between. Once a function calls b function, the control will remain in b function until the list of function is completed. However, things work differently with cooperative functions. With cooperative functions, if we have a function called a function, which is calling b function, the control will be transferred to b function. In b function, it will do the same job and it will say, "I'm done for now, you can continue." The control will transfer back to a function, and a function will start executing from the point where it left. It will say, "Okay, I'll do something," and then after some time, it will say, "I'm done, you start." Then the b function will say, "Okay, I will do 2 and 3. And then it will say, "You know what, it's your turn now." The control will again transfer back to a function, which will say, "Okay, I will do the rest of my work," and after completing the job, it will then ask b function to complete the rest of its work. Then b function will say, "Okay, I'll do 5 and 6. It will complete and return, and the control will then return back to a function, which will complete. Now you can see the kind of cooperation happening with these two functions. The control is transferred to and from A function to B function without changing the context and without executing the function completely on its own. Each of the functions actually remembers where it left off. And while resuming the functionality, it resumes the same point. Moreover, if you find this useful, there are also even better options during cooperations. We can also pass around values. For example, if you have a function which is calling B function, which means the control is transferred to B function comes up and does something, and after that it says you can continue with value 100. The control transfer back to A function and it says thank you for value 100. It does something and it says now you can continue with value 200. The control is then transferred to B function and says thank you for value 200, and then it continues the passing of values between A function and B function. It will continue as long as you want, or as long as it makes sense without breaking away with the context of each function. So, this is what coroutines are. Different programming languages have different syntax and different ways of doing this. However, yield keyword is most commonly used in Python, JavaScript, and other programming languages. So that sums up our topic for this week. Thanks for watching.